right, so I'm happy to introduce John Conway, who will start with his first lecture on the genus of quadratic form.
Yes, well, today I'm actually going to talk about the rational case, okay? And I'm going to make absolutely sure that at the end of this, you understand how to tell whether two forms are rationally equivalent. And it's very easy. I bring you a new message, really. John Hanke presented, except that he missed out some details, the traditional theory of rational quadratic forms. I'm going to give you a non-traditional theory, but then I'm going to explain how it's related to the traditional theory. So, I want you to know everything. Okay, so I'm going to take a particular rational quadratic form with this matrix. I put even numbers on the diagonal and odd numbers off the diagonal, not for any special reason. And then I'm going to show you how to diagonalize it, if you don't already know. This was with respect to a basis E1, E2, E3. E1, E2, E3. And then I'm going to use a new basis, which is E1 minus a half, E1, E2 minus a half E1. Can everybody see anything? Can anybody see anything? And E3 minus 3 halves of E1. Why were those numbers chosen? Because a half of 2 is 1. So I'm going to subtract a half the first row from the second row. Well, that will make it 7 over 2. Well, we're working over the rationals, that's okay. It doesn't matter, it's not an integer. And 5 minus 3 halves is also 7 over 2. And then I'm going to do 3 halves of the first row from the third row. That'll produce 0. That's why I made it 3 halves, 7 halves. It automatically produces, in this bottom 2 by 2 piece, a symmetric matrix. Now, this is actually the matrix of the quadratic form referred to two different bases, namely the old basis E1, E2, E3, and the new basis E1 prime, E2 prime, E3 prime, which are certain linear combinations of E1, E2, E3. And now I'm going to do put E1 prime, E2 prime, E3 prime here, and that means I do the corresponding column operations. Well, I subtracted a half the first row from the second row, so I subtract a half the first row from half the first column from the second column. And then I subtracted 3 halves, so now I subtract 3 halves of the first column. And you notice this third matrix doesn't look very different from the second matrix. All I do in the end is just cross off those numbers. And later on, when we get a bit faster at it, that's the way we'll do it. So we don't need to write down these hybrid matrices. But this is the new matrix with respect to a new base. And then I'm going to do the same thing. I now copy E2 prime. E2 double prime is E2 prime minus, oh, curses. I was saying something that wasn't true. E3 double prime is E3 prime minus E2 prime in this case. These numbers 7 over 2 happen to be equal, so it goes 7 over 2, then 0, and then minus 2. 3 over 2 minus 7 over 2 is minus 2. Sorry. And then I do the corresponding thing. I do the column operation, subtracting the second column from the third column. And there we have a diagonal form. Every quadratic form can be diagonalized. There's a little hiccup occasionally, but, let's work from here. Now, suppose we now have, by the way, this quadratic form, I write as square brackets 2, 7 over 2 minus 2. Okay. So every rational quadratic form can be diagonalized. Like the other people, I'm going to suppose that the determinant isn't zero most of the time anyway. Okay. Right. Well, now let's take a quadratic form that's quite long. Oh, by the way, yes. I'm free to multiply by non-zero squares. So if this was with respect to E1 double prime, E2 double prime, E3 double prime, then I'm going to multiply this by 2 squared. And I've got 2 E2 double prime. You should think of these as the inner products of vectors. So I can always make my entries integers after I've done this. In fact, I can make them square free integers, but I haven't bothered. Okay. Now, how do we get the signature? This is the traditional signature. I'm going to have to hyphenate that word. The traditional signature. Well, we take the signs of these numbers. Only I'm going to call those the -1 parts of the numbers. It's a big deal for me. -1 should be considered as a prime. Unfortunately, by the way, when Hasse first introduced these funny additional primes, he called them unit primes. Nowadays, somebody foolish, I don't know who it was, has changed them to being called infinite primes. I'm going to declare that that infinity is a synonym for -1. Okay? And you'll see, I hope you'll see. If you're not, I mean, you know, people sort of think it's silly of me to use -1 for this prime. They really do. Well, it's not silly. It's silly to use a stupid, unrevealing notation when you can use a better one. It really is. Well, I'm going to say several things like that. Okay, so there's sigma, only I shall call it sigma -1. Okay, I'll miss out 2 for a moment. And now, I don't know if this is going to work. Oh, sorry. Curses. 1 minus, those shouldn't have commas in between them. They should just have signs. And that's 0. And it's the -1 signature. Okay. Now, you know, one of my great discoveries is that there are more signatures. And damn it, this form is not a very good form to use. Well, never mind, I will. I'll continue. Let me say how you find the free signature. I just take, well, for this form, I take the sum of the 3 parts of the things instead of the -1 parts. However, that's not really what I do in general. I'll put a little 0 here and a little 0 here. And I'll explain what you do later. This concept, so the signature here is 1, 1, 3, that's 5, 6, 7, 10, 11, 12. It's congruent to 4 modulo 8. It's only defined modulo 8. And then the 5 signature, I'm sorry, this is not a 1, 1, 1. Well, excuse me for the hasty writing. Again, this is +0. This is 4 mod 8 again. Okay, I have obviously got to do one more case. 1, 1, 1, 1, 1, 7 and 1 is 6 mod 8. I'll define sigma 2 later, but I don't need it. Okay, but I think now I had better take a case where, I mean, this form looks very nice, but it didn't actually involve the adjustment. Okay, so instead I'll start with -1, +2, -3, +4, -5, +6, -7, +8. And I'll do the signatures. -1, I will just write down the terms to be added. So that's 0. This is sigma -1. For sigma 3, 1, 1. Ah, good, we're going to get something here. 1, 1. And now we have to add the 4s in. Sigma 3 is 4 again. Sigma 5. I'll tell you what the rule is in a moment. Am I? Oh, right, okay, well that doesn't matter really. But anyway. 4 mod 8. This is 5 plus 0, 7 plus 4. 1, 2, 3, 4, and that 4 cancels is 2, sigma 7. And the other sigma p are all 1, 1, 1, 1, 1, 1, 1, 1, which of course is 0 mod 8. Okay, I'll tell you what it is now. I write down here the p part of the number, but then I add 4 if the p part is an odd power of p. Let's say plus 4 if the p part is p to the odd and the p prime part is a non-residue, non-square mod p. So 2 is a non-square mod 3. So the p part was 3 here, which is 3 to the odd power. Oh, but yes. So I add a 4 in that case. So let me say I call this for anti-squares, i.e. for anti-squares mod p. I mean, if a number, if the p part is p to the odd, then the p part isn't a square. Okay? And if the p prime part is a non-quadratic residue, then the p prime part isn't even a square mod p. So this fails to be a square for 2 separate independent reasons. It's antithetical to the notion of being square. So has everybody got it now? These things are generalizations of the ordinary signature. Very simple generalizations of the ordinary signature. And now the assertion is 2 quadratic forms are congruent modulo the rationals if they have the same determinant up to square factors and if these p signatures are the same. Well, absolutely the same in the case of the -1 signature and the same modulo 8 in the case of the p signatures for other primes. There is a concept of 2 signature. We don't need it for that statement. That's a very, very simple thing to do. It's easy to work out. You don't need to take a whole lot of Hilbert norm residue symbols and multiply them all together when you don't even know quite what they mean. You just add these things. Okay, I'm not going to prove anything. That's not because the proofs are hard. It's because I really want you to know what to do if you want to if you want to tell whether two quadratic forms are equivalent over the rationals. Oh, let me say, suppose you don't only want to tell whether they're equivalent over the rationals. You want to tell whether they're equivalent over QP, the p-adic rationals. Well, you only take sigma p in that case, together with the determinant, okay? Sigma p is the one invariant. Now, it's rather funny. It takes values modulo 8. And we thought you needed only a function that took just two values. John Hankey gave the traditional presentation last time. He had a thing called the Hasse invariant. I think one should really call it the Hasse-Minkowski invariant for a good reason. What Hasse did was very much less than what Minkowski did. Minkowski wrote down a whole lot of invariants for quadratic forms. Hasse, he wasn't interested in just the rationals, he was interested in equivalence over the integers. But a lot of his invariants worked over the rationals, and Hasse just observed that he took off those invariants which were still rational invariants of rational equivalence, and then he did something. He proved that they were complete. But the idea of the invariants for rational equivalence, which, you know, you couldn't get invariants which were complete for integral equivalence. Right. However, we live in a world where, sadly, there's the traditional treatment in all the books. And you will want to know how to read the books and understand what they're really saying. Okay, and when you read the books, by the way, you will find that there are at least 4 things called the Hasse invariant, or the Hasse-Minkowski invariant, or the Minkowski unit, or various other things. And they all take values plus and minus 1 only, and they're all different. And so, listen, if you say the Hasse-Minkowski invariant, you're not defining anything, okay? Unless you say, according to Jenkins and Shapiro, you know, and then ... and then you have to work out. I'll tell you what they really are now. Here's the way to do it. You take your standard form. Well, let's have a way of let's call it your Hasse-Minkowski invariant. You can all have your own. Roughly speaking, that's what different mathematicians have done. Okay. Here's how to define it. To define your Hasse-Minkowski invariant, select for each d is a determinant, a standard, well, let's call it not a standard, your standard form of determinant d. And by the way, and given dimension too. I'm not going to mention the dimension, all right? Then, your invariant of f, let's call this the standard form f sub d of determinant d. Your invariant of f is plus 1 if f is equivalent to your standard form, p-adically equivalent. This is really QP equivalence, and minus 1 if not. You know, we know that there are just 2 forms of a given determinant. You know, the form with value plus 1 and the form with value minus 1. Here's how to get them. That's very simple. Okay, so there's no highfalutin nonsense in here. Let's take a standard form. My standard form, but it's not really, will be Well, it's the obvious one. 1, 1, 1, 1, 1, D. That's nice and easy. So my invariant, which is perhaps it is the most common form of the Hasse-Minkowski invariant. My Hasse-Minkowski invariant is the one which makes that have value +1 and other things have value -1. Right. Well, now what do you get? I mean, what am I trying to say? How do we work out what my Hasse-Minkowski invariant is? So let me just give you one. My Hasse-Minkowski invariant for p equals 3 is, now this is for, hang on, -1, 2, -3, 4, -4, -5, 6, -7, 8. Let's say 4, that is, well, do you remember what I got here? Let's just say for which, I don't want to work it out again, the 3 signature is congruent to 4. Well, what is my standard invariant? Well, look, this form is 1, 1, 1, 1, 1, 1, 1, factorial 8. Do you understand me? That's my standard form of the same determinant as this one. Ooh, what on earth is factorial 8? It's, well, let me try and work out what that is. It's got 9 times, and then the product of all these other numbers, which is 1, 2, we can forget the sign, 1, 2, 1, 4, I've got 8 so far, and 5 is 40, 2 again, now I'm only taking the 3' part, is 80, 80 times 56, well, let's write it as 80, 56. 80 mod 3 is -1. 56 mod 3 is also -1 mod 3. So this is 9. So wait a moment. So sigma 3 is 7 plus 9, which is 0 mod 8. Okay. Oh, I'm writing off the page. Well, I'll show it up. Okay, so this form gave sigma 3 equals 4. This form gave sigma 3 equals 0. So they're not equivalent. Okay, and so my Hasse-Minkowski invariant is -1. Okay, you understand me? I worked out the invariant for this form. I worked out the sigma p for this form. I worked out the sigma p for this other form. They're not the same. And therefore my invariant for this thing is -1. That's the standard one. Now let's talk about Hilbert norm residue symbols and so on. No. You see, sorry, it depends whether we're working over the rationals or over Q3. Working over Q3, there are just 2 forms. So if I say the invariant is the same, the form is the same. You know, one is the form with value +1, which is my standard one. The other is the other form, whatever it is. For which, okay. If we are, however, working over the rationals, then we need all the sigma p to be the same. Okay. However, that seems to be infinitely many primes, but you'll notice the value. Suppose your number is prime. Suppose your matrix entry is prime to p, then its p part is 1. So you just get 1 and 1 and 1 and 1 and 1 and 1, and sigma p is known to you. It's the dimension. Okay. Right. Now, what on earth is this Hilbert norm residue symbol? Well, so what happens? What am I trying to say? Sorry, Oh yes, and what I want to say is one of the properties of the Hilbert norm residue symbol, which I'll just say Hilbert symbol, and let me call it A, B, subscript P. It has slightly different notations, is +1 if the quadratic form A, B is the same as 1, AB. This is just exactly the same as the general thing. If it's the standard form of its determinant, periodically, then it's 1, and -1 if not. So what does that mean? Well, this one, no, I don't think, okay. Right, it's multiplicative. Well, and another word for it is bilinear. And what does that mean? A, B, C is equal to A, B, A, C. That's linearity in the second variable. It's rather funny because its values are plus and minus 1. So linearity is written in a multiplicative way. It's bilinear. Okay. So, we get the funny thing, and symmetric, by the way. So we get the funny thing is, we're really talking about symmetric bilinear forms, and the invariant is a symmetric bilinear form. Okay? It's a funny thing. Well, why can't we associate a quadratic form instead? And I'll tell you what the quadratic form is. Look at what the invariant for this is. Oh, sorry, let me make it capital A. Well, I'm going to take A to be p to the alpha times little a, where this is the p part of A, and this is the p prime part of A. Okay, and what did we do? We took it to be p to the alpha. Remember, I take the p part plus 4 if alpha is odd and a Jacobi p, or a Legendre p if you like, is -1. What is that? Well, this is the p prime part Jacobi the p part. Okay, so let me just say what this means. This is an additive form of the Jacobi symbol. And the Jacobi symbol is, I write with round brackets. It takes value 0 if this thing is +1, and takes the value 4 if this thing is -1. It takes the value 0 mod 8 and 4 mod 8. So all I've done is taken a new group of order 2. Instead of the group consisting of plus and -1, which ordinary mathematicians use, we take the group of numbers modulo 8 that happen to be 0 or 4. That's a group of order 2. You don't have to worry about that. And this is what it is, you see. I'm basically supposing you know what the ordinary Jacobi symbol is. It's defined to be the product of Legendre symbols. So this object here means AP raised to the power alpha. This object is AP times alpha, because we're writing it additively instead of multiplicatively. Okay. Now I want to sort of say there's another version of the invariant, which is this. Let's consider sigma p of A, B, C minus the dimension of A, B, C. I chose sigma p to start with because that's a generalization of the traditional signature, okay? And I thought you'd find it happy. But you'll notice that for almost all p, sigma p is the dimension, okay? So we might as well sort of normalize by subtracting the dimension, and then we'll have the assertion that for almost all p, sigma p is 0. And what is this? This is p to the alpha plus the Jacobi symbol plus p to the beta plus the Jacobi symbol plus p to the gamma times the Jacobi symbol, etc. Minus 1, minus 1, minus 1. Okay, so the typical thing is, so I'm going to call this the p-excess. This is, well, let's just say equals p-excess. So I'm going to write it as epsilon p of A, B, C, but we might as well just do it in one dimension. Epsilon p of A is p to the alpha minus 1 plus this thing. And that is the p part of A minus 1 plus the p prime part of A over the p part of A. And it's additive in the dimension. Okay, that's a very, very fundamental thing. I'm going to assert this is a quadratic form. This is absolutely fantastic. And what it is the quadratic form of which the Hilbert symbol is the bilinear form. Quadratic forms correspond 1-to-1 in general, if you're over a suitable ring, to symmetric bilinear forms. This quadratic form is the one that gives the, whose symmetric bilinear form is the Hilbert symbol. Now, this is really very strange. N to n minus 1 is a quadratic form from odd numbers to numbers, well, let's say to z mod 8z, numbers modulo 8. This is absolutely fantastic. Let me remark that the p part is an odd number. I haven't introduced p equals 2 yet. So the p part is an odd number. I'm going to assert that this and this are separately quadratic forms. So let's find out. What does that mean? What does it mean to be a quadratic form? It means that this sort of polar version, f of, well, I'm going to be writing it odd numbers under multiplication. Okay, so i.e. f of xy minus f of x minus f of y is bilinear. That's the condition. That's the condition for a quadratic form. Okay, but what does that mean? Well, this means, if you think about it, i.e. f of x into yz minus f of x minus f of yz equals f of xy minus f of x minus f of y plus f of xz minus f of x minus f of z. So the condition for being a quadratic form is this identity, which has got numerous terms in it. It's actually, 2 of them cancel. It's got 7 terms in it. What it is i.e. f of x, y, z minus f of xy, and then there are three terms like that, xz minus f of yz plus f of x plus f of y plus f of z. And there's really a minus f of 1 there, but f of 1 is 0. That's the condition for a quadratic form, if you take out everything else. Well, now let's think of what happens here. For us, they're odd numbers. Let's say they're p. Can we think of what good names for odd numbers? MN, RST. So f of xy, oh no, it's x, y, and z are good enough. And these are odd numbers. X, y, z minus 1. My function is n minus 1. Minus x, y minus 1. Minus x, z minus 1. Minus y, z minus 1. Plus x minus 1. Plus y minus 1. Plus z minus 1. And then minus 1 if you like. I sort of feel it's more natural, is 0. But this thing is just x minus 1, y minus 1, z minus 1. And what I told you was that the function that takes n to n minus 1 is a quadratic form with values. It's quadratic form on the odd integers with values in the integers mod 8. This is 0 mod 8, if x, y, and z are odd numbers. That's the key to something really rather astonishing. Okay, so that verifies that this term defining my function is quadratic. It's a quadratic function of the odd number. This is also quadratic. Now, why is that? Well, that's the product of two linear functions. The Jacobi symbol is linear in each variable. Okay? It's got an odd number at the top and some other number, an odd number at the bottom and some other number at the top. And it's linear in each one of those. So this is the product of two linear functions. That's quadratic. Okay. That's a quadratic form. It's absolutely astonishing. Okay. Now you want to know what the Hilbert symbol is. It is Hilbert symbol. It is this function. So what on earth can I call that? I'm going to call it from epsilon p, and epsilon p, remember, is defined by the p part of A minus 1 plus this additive version of the Jacobi symbol. Okay, is epsilon, it is, let's call it A, B sub p. It's epsilon p of A minus plus epsilon p of B minus epsilon p of AB. Okay, I seem to have defined it the wrong way round, so I'll change the sign of it. But it doesn't matter because its values are multiples of 4. Its values are 0 or 4. This is the additive form of the Hilbert symbol, which takes values 0 and 4 instead of 1 and minus 1. So there's what your Hilbert symbol is. And remember that the Hilbert symbol of this is, this is equal to the Hilbert symbol of the standard form of the same determinant. Sorry. I'm sorry, I didn't do the right thing there. It's epsilon p for that form minus epsilon p for the other thing. I got it wrong. So it's the difference between your form and the standard form of the same determinant. This is how I told you to compute to compute equivalence. Now let's discuss what happens in general, let's have a look at what the Hilbert symbol let's work out what this symbol is. Well, I'll tell you what, I think I'll just stop it at 4 variables. Okay. What do I get? Well, I think I'll write Q for the quadratic form. This is Q of A. This is my famous quadratic form here. Q of A plus Q of B plus Q of C plus Q of D minus Q of A, B, C, D, because Q of 1 is 0. Now, what is Q of A, B, C, D? It is, well, let's just wonder what that is. This is Q of A plus Q of B, etc., plus Q of C plus Q of D, plus the inner product of A and B, plus the inner product of A and C, plus, etc., plus the inner product of B and C. These are 6 terms. And then when you look at that, I've taken away that, and it doesn't matter whether I have minus or plus here because the things are just 2 valued. So what it is the product of these Hilbert symbols. Oh, well, no, for me it's the sum of these Hilbert symbols. You understand me? So the situation is, if you use Hilbert symbols to do this, you are really being silly. You're giving yourself a lot more work to do. You have, because the Hilbert symbol is only a bilinear form, you have to evaluate it at a whole lot of places. You have to evaluate it as essentially a square number of terms. And then you don't quite know what it means, really, either. I mean, if you're a typical person doing this thing for the first time, you know, because it's defined to be something or other if something's isotropic and something else if it's not, and it takes you ages to work out any individual one of them, okay? And you've got to take the sum of a triangular number. Well, you don't need to do it. If you use this quadratic form of mine instead, then you're getting the same thing by just adding n terms. And moreover, you have the following fact. The quadratic form in f direct sum g is the quadratic form of f plus the quadratic form of g. Obvious. What's the corresponding statement in terms of Hilbert symbols? The Hilbert symbol of f direct sum g is, it's the Hilbert symbol of f plus the Hilbert symbol of g, plus all the inner products. I mean, this, okay, plus or minus, it doesn't very much matter, but what you have to do is, well, I'm sorry, I'm writing, let's switch to writing it multiplicatively again, times all the inner products, and the inner products are det f, det g, the Hilbert symbol of that. This is because it's not linear, it's quadratic. This is bilinear, but anyway, it's not a quadratic form. So you have this correction term, which is essentially the inner product. Let's discuss what happens here. F is F1, F2, F3, and G is, say, G1, G2, G3. And what do we have to do? We have to take the product of all the Hilbert symbols. I mean, to get this one, we have to take the Hilbert symbols of the F's with each other. That's a triangular number. And the Hilbert symbols of the G's with each other. And then the product of Fi, Hilbert symbol Gj. Product over I and J. But that is F1, F2, and G1, G2, because the Hilbert symbol is multiplicative, and that's determinant F, determinant G. So if you want to take the Hilbert symbol of a direct sum, you take the Hilbert symbols of the two factors and combine those. Sorry, not, well, I'm sorry, whatever you want to call it. I don't know. I think I've sort of almost said enough on this topic. I'm saying it over and over again. Okay. I want to say some other properties of this form. I think I will call it, I don't want to write epsilon p all the time. I think, oh, maybe I'll write it epsilon. I'll write epsilon p. So properties of epsilon p. Well, I think I want to just remind you first that, how can I say it? Epsilon p of A plus epsilon p of A, this is just to finish off, plus epsilon p, etc., minus epsilon p of A, B, C, is a Hasse-Minkowski invariant. And that's the best way of computing it. That's property number one. Property number two, I'll just say it's quadratic. Property number three is epsilon p of F, direct sum G, is epsilon p of F plus epsilon p of G. Property number four. Property number four was the first one I was going to write down, and I thought I should write down all these easy ones first. What is it? Property number four. Forgotten the very one that started this off. Oh, well, there's no hope for it, is there? I'll come back to it. Oh, yes. Aha. It generalizes to epsilon pi, where pi is a set of primes. Well, initially they're going to be odd primes. Okay, so let me write this. Epsilon pi of A is the pi part of A minus 1 plus the Jacobi symbol of where the numerator is the pi prime part of A. That's the same definition, essentially. But now you're to really think of the things. And here's the wonderful thing. And wonderfully, if pi 1 and pi 2, sorry, let me put a comma there, are disjoint sets of odd primes, then epsilon pi 1 and pi 2, sorry, let's say pi 1 union pi 2 equals pi 3. Then epsilon pi 3 is epsilon pi 1 plus epsilon pi 2. It's not only linear in the quadratic form, it's linear in the set of primes, which is amazing. And this is QR, quadratic reciprocity. And let me just show it for you. It's really beautiful. All right. So what am I going to do? I'm going to let A be P, Q, R, where this is the pi 1 part, this is the pi 2 part, and this is the rest. Okay? And then let's look at what epsilon pi 1 of PQR is. Well, of A. No, well, let's do it PQR. Right. Well, that is the pi 1 part minus 1. Okay? Plus the Jacobi symbol of the rest. Okay? This is the pi 1 part of A on the bottom and the pi 1 prime part of A at the top. What's epsilon pi 2 of PQR? Well, this is Q minus 1 plus PR Q. And what's epsilon pi 3? Well, this is PQ minus 1. Okay? That's the pi 3 part plus the pi 3 prime part. Okay. Well, I want to carry on, and so I'll carry on like this. This part is P minus 1 plus QP plus RP, because the Jacobi symbol is linear in each variable, so it's linear. This is Q minus 1 plus PQ plus RQ, and this is PQ minus 1 plus RP plus RQ. Now, what I want to do is check that this is equal to this plus this. So that's what I'm going to do. I'm going to subtract the first two lines from the third line. And look what I get. I get P minus 1, Q minus 1 for these terms. And then this will cancel that, and this will cancel that, minus QP plus PQ. Now you know that well, I trust you know, you've heard of this famous theorem of quadratic reciprocity, the sum of two mutually inverse Jacobi symbols, well, I state it as a sum because my Jacobi symbol is additive, is equal to this. This is precisely quadratic reciprocity. Let me talk a little bit about the folly of using the name infinity for the additional prime. This proof works. In fact, I was supposing minus 1. I was allowing an odd number to be minus 1. Okay? Let me remark that what happens... sorry, I'm trying to say something. I mean, in the theorem of quadratic reciprocity, you can allow one of the two primes to be minus 1. Minus 1 doesn't behave badly in any way whatsoever. So we have the theorem that the two Jacobi symbols minus 1p and p minus 1. P minus 1 is trivial, by the way, because what? Yes, let me just sort of say. I'm supposing that p is a positive odd prime. This one is 1 if p is congruent to 1 mod 4, and minus 1 if p is congruent to minus 1 mod 4. This one is 1. And let me just discuss that for a moment. I haven't really discussed what should happen if you take minus 1 in the denominator. What it really means is p a square in the real numbers? The real numbers correspond to the case QP for p equals minus 1. Well, every positive prime is a square in the real numbers. So this is just automatic. And QR still holds. Minus 1 is not exceptional in any way. This proof of QR, oh sorry, it wasn't a proof of QR, it was a proof of something else. The proof applies if minus 1 is one of the numbers. It's easy. This minus 1 is in no sense exceptional, except for the definition of what the p-adic numbers are. So p equals minus 1. Then that's slightly different. But in all of the algebraic manipulations I'm behaving, minus 1 is in no sense exceptional. Now, what about 2? I mean 2 as a value for a prime. 2 is exceptional in a certain sense. Well, what we do more generally, what if 2 is contained in one of my sets of primes? Okay, it was always a set of odd primes before. And remember that the fundamental thing that I used was really that if 3 numbers are odd, then the product of their minus 1s is 0 mod 8. I use that very fundamentally. That's not true if one of the numbers is 2. Well, the answer, we define epsilon pi so that epsilon pi plus the complementary set is 0. It seems like cheating. But it's not. And I want to say cheating. Well, maybe. Maybe it's cheating. It gives the fact that the sum over all primes of epsilon p is 0. Well, yes, in a way it's cheating, but epsilon 2, so defined, is a 2-adic invariant. So, okay, so let me discuss that. What's epsilon 2 dashed of A? Okay, well, it's the 2 dashed part of A minus 1 plus the, which way around is this? The 2 part of A, Jacobi, that's the definition of epsilon 2 dashed. And so epsilon 2 of A, oh, well, let me say this is the odd part of A minus 1 plus, now we've got the odd part of A. The Jacobi symbol is normally only defined when the denominator is an odd number, and then the 2 part of A. Okay. So epsilon 2 of A is 1 minus the odd part of A, minus, it doesn't matter whether this is minus or plus. These Jacobi symbols all take values 0 or 4, so they're their own negatives. Minus the 2 part of A, the odd part of A. Right. Well, look, this is, how can I say it? It only uses things that are two-adically invariant. In fact, so let me talk about it. So epsilon 2 of f is the dimension of f minus the sum of the odd parts of the various terms in the, so f is supposed to be the diagonal form a, b, c, minus 2 to the alpha a. So, well, okay. So let me say what it is. I mean, let's do it for one of these forms. Minus 1, 2, 3, minus 3, 4, minus 5, 6, minus 7, 8. Okay. So what I've got to do, it's easier if I discuss epsilon 2 dashed or sigma 2 dashed. No, epsilon 2 dashed. Sigma 2 dashed. Sigma 2 dashed. Sigma 2 dashed, I take the odd parts. Okay, and now I've got to discuss when the 2 part. I mean, I'm going to discuss what I have to add to this. For this, a 2-adic anti-square is something whose, well, let's say. Add 4 for a 2-adic anti-square. And what that means is the odd part is 8n plus or minus 3, and the 2 part is 2 to the odd. Well, here, most of these numbers were odd numbers, so the 2 part was 2 to the even. Some of them had 2 in just once, but then the cofactor was 1. Cofactor here is 1. Cofactor here is 3 modulo 8. Ha ha! Okay. That's it. So what is it? It is minus 3, 1, minus 2, minus 7, plus 7 is 0. So it's minus 6, which is 2 mod 8. Okay, so epsilon 2 prime is that minus the dimension, which is still 2 mod 8. And then epsilon 2 is minus 2. Or if you like, 6 mod 8. Anyway, now we have a very simple thing. I mean, don't worry about 2. Because you don't need to worry about 2, because epsilon 2 plus the epsilons for all the odd primes adds up to 0 anyway. So if you get the odd primes right, you're getting 2 right automatically. So what's the summary of this? If you want to know, I mean, an invariant of a quadratic form is its p signature, okay? And that's the only invariant of p-adic equivalence apart from the determinant. So let's always understand that we're working with forms of a given determinant. We know the determinant. And perhaps I should say we know the dimension as well. Those are invariants. Then the only other invariant is the p signature. But if you like, you can take the p excess, which is the p signature minus the dimension. The p signature is very, very easily defined. Now, if you want to convert to anybody else's invariant, and in particular to the fairly standard one using the product of Hilbert norm residue symbols, you just evaluate the p signature at your form and at the standard form of the given determinant. And for the most common definition of Hasse-Minkowski invariant, which is this exclusive product of all the Hilbert norm residue symbols, for the most common definition, the standard form of given determinant is the one that goes 1, 1, 1, 1, 1, 1, D. So, you know, you ought to understand what this means anyway. I mean, the Hilbert norm residue symbols, you multiply it up, all up. There's some complicated nonsense. You get plus or minus 1. What's it mean? It just means, are you equivalent to the standard form or not? You know, to 1, 1, 1, 1, 1, 1, D. The definition of the Hilbert norm residue symbol, it's normally given in something you don't understand. It's something or other is isotropic. The Hilbert norm residue symbol is plus 1 at A and B if the form AB is equivalent to the form 1, comma AB. Now, by the way, it's equivalent to the form 1, comma AB means it represents 1. Just represents the square, because if it represents 1, the second term can be just worked out from the determinant. It can be made to begin 1. So, you know, it's not mysterious hocus pocus nonsense. It's just trivial. Okay? I haven't proved that these things are invariant, but I have shown to you that they have this wonderful property. Quadratic reciprocity is equivalent to the assertion that the sum of all the epsilon p over all primes is 0. Okay. Now, it turns out that's a very fundamental thing. That's the only relation. If you give me a whole lot of forms, but you're only specifying them p-adically, okay, and all these forms have determinant, the same determinant and the same dimension, and most of them are equivalent to the standard form of that determinant and dimension. So, in other words, there are only finitely many variations. Then the only relation that you have to have in order that there exists a global form with those invariants is this thing which is traditionally called the product formula. I can't call it the product formula because for me it's a sum formula. Okay, I don't want to call it the sum formula because that sort of pretends it's different. I want to call it the global relation. The global relation is that somehow all the pieces not. Now, you know, traditionally everybody who was an expert in the subject knew that the effect of the global relation was to impose a condition on the signature mod P, mod 8. So, I mean, it's responsible for the wonderful fact that many of you will know that if you take an even unimodular quadratic form, its signature is 0 mod 8. In this way of treating it, it's obvious it's a signature condition, because one of the terms in the global relation is the signature. And the global relation says this total sum is 0 mod 8, so you can regard it as specifying the signature mod 8. Okay, so what is it? Minus 1. I really don't want you to call that pram minus 1 infinity. I mean, let me say, you know, it's not sensible to do it. It's not sensible to use a stupid notation just because it's conventional and traditional. It really isn't. It obscures things. Now, let me sort of say, look, I have this formula. As whatever it is. It's meaningless if I put an infinity in there. And it's meaningless if I put an infinity in there. Okay. You can go on doing that if you like, but you know, you're being stupid and you'll not notice various things that are obvious. I mean, the minus, you know, Well, it really is stupid, folks. I mean, don't do it because, you know, these unfortunate people didn't know what they were doing when they did this. They thought it was a matter of just sort of trivial notation. It's not. It obscures the truth. And, you know, I don't mind being thought of as silly, but I'm not silly. I don't want to be thought of as silly by silly people.